Hello and welcome to this Chemistry World webinar, It's a Gas. I'm Natalie Starkey from Chemistry World and I'm here with you for the next hour. Well, I'll be joined by author and scientist Mark Miodownik to hear all about his new book, looking at the invisible world of gases. I'll introduce him properly in just a moment. But before I welcome Mark on screen, I'd just like to let you know that this webinar is being recorded. So if you miss anything or you just want to re-watch the webinar or share it with friends, then do look out in your inbox in the coming days for a link to the recording. So let's welcome Mark on screen now. Just get his camera on. Hi Mark, how are you doing?
Hi.
Great to have you with us. So I'm just going to tell the audience a little bit about you. Now, Mark is a Financial Times Master of Science and chosen by the Times as one of the 100 most influential scientists in the UK. Mark is Professor of Materials and Society at University College London, where he's also Director of the Institute of Making. Mark regularly presents BBC television and radio programmes on science and engineering, such as Everyday Miracles and Materials, How They Work. A new BBC Radio 4 series with Mark comes out very soon, Glued Up, the Sticky Story of Humanity. Now today we're taking a look at Mark's new book, It's a Gas, the same name as the webinar, which actually only came out yesterday. So we are very lucky here at Chemistry World to have Mark joining us today to share more about the science of gases. The book has had some lovely things said about it already, and so you'd be well placed to grab a copy very soon from wherever you normally like to buy your books, but do remember to support your local independent bookshop if you are lucky enough to have one. Just to let you know, the book will be published in the USA on September 17th by HarperCollins. I know we've got quite a big US audience, so you may have to just hold tight for a little while till you can get a copy. Now, a really great thing about Chemistry World webinars is that they're interactive, which means you can ask questions about any aspect of what Mark covers today, and we love to hear from our audience. So Mark's getting ready to answer any burning questions you have about today's topic. To post a question for Mark, please do it whenever you're ready throughout the webinar. You won't usually be able to see other people's questions in the questions box, but myself and the Chemistry World team assisting in the background can, and I'll be able to put them to Mark towards the end of the webinar. So without further ado, let's hand over to Mark to hear much more about It's a Gas. Brilliant, and it's all ready to go.
Great. Okay. Well, hello everybody. It's great to be here, and thank you so much, Natalie, for the invite and Chemistry World. Yeah, I want to talk about my new book, It's a Gas. It's obviously about gases, and it's quite an intimidating topic, really, to kind of try and encompass in an overarching kind of narrative. And so what I kind of in the end went for is to kind of first of all just really think about how we interact with gases as humans, like our sensory world, breathing, I guess, and smelling, and then sort of also I wanted to link it with the fact that when we evolved on this planet, which we'll talk about in a bit, which is the rise of oxygen and evolution and all the gases in the atmosphere and how we became breathing animals, I wanted to kind of conjure up in the book a strong sense of that our sort of interior world, our dreamlike world, our subconscious world has taken with us our past experience of gases and the gas phenomena that we evolved with, so the winds and the kind of mists and all the kind of actions that we attributed to those phenomena were at first put onto things like gods and ghosts, and there were just names for so many wind gods and fire gods, and I want to sort of bring all that in to the start because I think it kind of really informs why we ended up first of all ignoring gases, because it's so hard. Most of them invisible, tasteless, they don't smell of anything. So it's actually as a kind of substance, they're not an easy way for science to get its teeth into, and actually the discovery of lots of gases is very late compared to things like metals and other solids and liquids. But then when we finally do get our teeth into them and we really do start to understand, we have the right tools to look at them, of course they start displacing our belief in all these mysterious entities that we hitherto attributed gas phenomena to, like ghosts and spirits and so on. So the book is infused with a kind of history of the humans and our thought processes, our unconscious, and then our sort of our growing understanding of the rationality of gases. But also, you know, we can talk about it in the questions, but I feel like there's still quite a lot of irrationality out there attributed to gas phenomena. And I think that's interesting. Why should that be? Is it because they're fundamentally invisible to us, and that however much we can really rationally get our heads around them and do experiments and harness the technologies, which I also talk about a lot in the book, the gas technologies, we still, at some level, we still have this kind of feeling that anything invisible is kind of spooky. Anyway, that's just a sort of preamble of the kind of the way the book has shaped up. And I hope, yeah, to get into some of it now. Okay, so yeah, which hopefully explains to you why I've got a picture of a fire, because I want you to go back to like our ancestors, like looking at a fire. A fire was so important for the development of humans, you know, from apes. And our mastery of fire is a key point in our evolution. And the kind of development of the idea of what fire is starts with the idea that it's an element. It's a fundamental element of the universe. There are 4 elements classically in the sort of Greek tradition, which are earth, air, water, and fire. And it's a mistake, obviously, that we know now that fire is actually a gas phenomenon. But I just want you to appreciate really that, you know, it's taken us a long time to understand that fire is a series of different gases interacting and combusting. And it's even quite late to understand that, you know, what we call combustion, which is a chemical reaction between oxygen and the kind of the vapors being released from, in this case, wood. So these are sort of, you know, methanes and carbon monoxides and some hydrogen. Those things, we didn't understand any of those gases. So it's not surprising that fire was thought to be this fundamental element. So you had fire early on, and there was obviously another gas phenomenon, which is wind. And it's easy to appreciate that wind is this huge overarching kind of thing that happens to us, you know, on the earth. And early days, this is a picture of a Polynesian sailboat, but that design is at least 2,000 years old, and it's still being made today. It's still being sailed today. You can make it from all the elements of an island in the Pacific. And the Pacific itself, the Polynesians, I mean, these are probably the best sailors that have ever lived. That whole area, the Pacific, is a third of the Earth's surface area. It's a water world, essentially. There's almost no land in it. And the people who lived in those areas, they had an affinity with the wind and a kind of appreciation of the wind that people who live on land and know the land very well and can navigate the land, and you know, it's perhaps more easy to understand that there's a landmark and it's paths, and you know, you can see woods and you can see mountains and hills and you can navigate and you can know a place very well. But how do you know the sea very well? Because on a calm day, there's nothing at all horizons to see, and on a day pictured here, there's obviously the cloudscape and the wind. But they were able to navigate thousands and thousands of miles, get from one island to the next reliably, no equipment, no navigational equipment at all. And so their affinity with the wind is not, I think, not to be unright. And they had loads of songs, and they could tell, they navigated by the stars at night, but they didn't have any written documents of the stars. But they also understood how to dead reckon. So they could tell how far they went by just understanding or feeling the strength of the wind and the setting of the sails, and they could accurately detect, and still can today, how far they go. So you know, the elemental world of our ancestors, you know, is dominated by the wind, by fire. Here's where technology starts to kind of harness wind in a different way. This is in Iran, and still functioning today. It's at least 1,000 years old. These are windmills, and these are an early version. So these are vertically set windmills, and they rotate. The wind blows reliably through them. they're just wood again, and a little bit of metal kind of pin-ins. And what you can't see, but underneath here are the grinding mills to grind the flour. You know, this is a very reliable, very robust. Again, you can make it from the local the mud, and you can make it. You know, you can get the stones and you can get the wood. And windmills became an increasing, you know, from sort of 400 or 500 AD, windmills become an increasingly prominent feature of cities and civilizations for doing all sorts of tasks. And this powerful element helps, you know, is an aid to humans, but it's also a foe. And there are loads of wind gods. There are wind gods in every language, and there are angry wind gods who throw storms, and there are the beneficial wind gods. I mean, there's the hurricane, which is a Mayan wind god, which is an angry god. But just to sort of play forward, like as kind of the age of sort of rationality hits, wind is no less kind of revered, and in fact trade between countries is hugely kind of enabled through basically building huge ships now, like an enormous sailboats and much better navigation, and being able to sail around the world and trade between them, but also to colonize and do all sorts of terrible things. But it's the wind, harnessing the wind, these elemental forces, that kind of allows humans to do this. So there's a kind of there is this moment where steam power sort of takes over, and it's a sort of, it's not that the Greeks and the Chinese didn't understand that steam was a powerful thing and that could be harnessed. In fact, they had rudimentary steam engines, but it just couldn't compete with wind. You needed a lot of fuel to make the steam, and then you had to carry it around with you, and that was expensive because fuel was always hard to get hold of, and the water was heavy, and wind was just plentiful and there, and except for when it wasn't, of course, on those calm days. But they put up with that. And in the case of grinding corn and so on, again, they could sort of grind when the wind blew, and then when it didn't, they just didn't grind, and they stored it, and that was how it worked. But there was this sort of sense, and this is the sort of 17th, 18th century, where technology is really growing in Europe, and there's a lot of scientific understanding, a lot of rationality going on, that actually steam is an opportunity for machines, and how to do it. And the first person who's really attributed this sort of actually making steam work for humans is a guy called Thomas Newcomen, who's a preacher and an engineer, and understands there's been a lot of previous experiments about this thing called atmospheric pressure, which is starting to be understood more, and there are instruments for measuring it. And this is the appreciation that there's 100 kilometers of air above us now, and this enormous body of air is pressing down on us the whole time. And you can measure that pressure, and when that pressure changes, the weather changes and the winds blow, and so that sense of understanding the wind comes along because of the barometer, which is one of the instruments that sailors then use to kind of know when to set sail and not go into a storm. But this understanding about the atmosphere and the atmospheric pressure then brings a different way of harnessing steam into play, and that is the fact that if you have a piston and a cylinder, if you fill the cylinder with steam, the steam at atmospheric pressure will be equal and opposite atmospheric pressure. But then if you spray a little bit of water into that cylinder and cool it down, all the steam condenses, and that creates a vacuum. And so the 100 kilometers of air above it pushes the cylinder down. If you then fill that cylinder with steam again from your boiler, and you pull the cylinder back up again, you have the same thing again. So every time the piston comes down, it creates a stroke of force, and that force is from the atmosphere. So this is called the atmospheric engine, and it's very slow, and you have to wait for the cylinder to fill up with steam again, and then you condense it, and you get this big clunk, and then it goes up again, and you get clunk. But it was power on demand. The wind didn't have to blow in order to, in this case, the first application was pumping water out of mines. And the very mines they were using to get the coal which was then one of these big, which was solving a problem for Britain at the time, which was lack of forests to get fuel and the growing population and the need for heating and cooking material. And here was a machine that could make it uninterrupted flow. You could keep getting the water out of the mines, you didn't have to interrupt that. And because you got the coal, you could keep even this incredibly inefficient machine, but it could just keep going because it was plentiful. And about 100 years goes by and people start fiddling with it. And James Watt famously kind of makes it much more efficient. But I just want to show you a video of that atmospheric pressure that I did in our just at home recently. So I've got steam inside that. I just lock the top. So it's the steam inside the can, and now it's sealed. Then I put it into the cold water, and because the steam inside is condensed, this is the atmospheric pressure pressing down. And so that's the force we're talking about. But instead of crushing the can or crushing the cylinder, it pushes the cylinder down. It's a much better way of using the force of steam than just as a jet. So, of course, pumping is one thing, and in fact, the steam engine was then used for manufacturing and for textile mills in the UK and lots of other things that could work 24/7, and that in a way was a very oppressive use of the technology, but it did create a lot of wealth. But the thing that people really wanted from the steam engine was a car, and it was recognized really early on. So this is an early French steam engine car. This is 1780s. And it's the first steam car we know of. And it was developed for the French military. You can see the big boiler at the front, and you can see the pistons, and it's an incredible, it's a cart basically with a steam engine attached. And if you look on YouTube, you'll see some videos of recreations of this. And it's an enormously cumbersome object. But it worked, it would go. But the French military in the end decided against developing it any further than this. What they really wanted was something to help them drag big bits of equipment to the front line and to help supply their troops. And it was competing at the time with horses and carriages. And this thing went slower than a horse, and any bad roads and it would veer off violently. It was very hard to control. It was very difficult, a very heavy machine. In the end, they didn't really see a future for it. And the state of the roads is hard to underestimate in making the steam car really unviable. Later on in Britain, the steam car gets a revival again, and it's the roads, it's the infrastructure that really stop it blossoming. So this is an early version, but people have this idea that steam can really give us liberation, that travel is something people want. But the heaviness of the steam engine is not a big handicap at sea. And this turned out to be the first real application that worked. And also it was a drop-in technology. So already there are ports all around the world. Britain at the time was the premier seafaring nation, had all these kind of connections, all these infrastructure for getting ships out to sea. But the one thing you faced at sea was coming in or up rivers where you wanted to go one direction, the wind wasn't blowing. So you could use steam in those moments. You didn't have to use it all the time. And it didn't matter that the steam engines were heavy or that you needed lots of fuel, because actually you have buoyancy. And so it doesn't, weight is not a really big problem. You just build a bigger ship. So the steam engine fits in with sail at first, and you sail when the wind's with you, and when the wind's not with you, you put the engine on. It's slower, but you still get there. And it was gradually seen to be a really important thing. And the benefits of being able to sail where you wanted to go at any time, any place, without the wind, having to rely on the wind, and especially coming upriver into estuaries, was recognized as being a huge benefit of steam. So steam engines become a big deal, but they become a big deal for transport at sea first. And then what happens is that there's someone, Robert Simson, who lets go of the idea of a car. And I think it's really interesting in the history of invention when you let go of something and you're open to something else. And what he'd observed was that the railways already existed in mines. Okay, railways were already a thing. But they were hauled by horses, and so you had this track infrastructure coming in and out of mines, and these tracks were often wood at the time, but they could also be iron, and iron was getting a bit cheaper. So the weight problem of a steam engine could be solved by having an engine, and what he was trying to solve was getting more coal out of mines quicker. So yeah, let's put a steam engine on a rail, and then let's pull it out of the mines. But for an experiment, he decided to also have a passenger carriage. Let's just see what it's like. Anyway, this experimental passenger carriage, because it's crazy. Like it feels like you're being, if you're a human on this, you're the equivalent of a bag of coal. You know, you're a commodity, and that felt kind of perhaps not something that anyone would want to sign up to. But it was so thrilling. It was so liberating, and it was so fast. And okay, so you needed to build this infrastructure anywhere you wanted to go, and that was obviously a lot of investment. But once you'd done it, you could pull a lot of people at one time. So you were now competing against a horse and cart. But whereas a horse and cart can only take 10 or 12 people, now you could take 1,000. And it's the beginning of public transport. And again, it's this sort of psychological moment where the whole public just says, we want this, build this, we're in. And also people can afford it, because the only way to run these profitably is if you have 1,000 passengers regularly every day. And so you have to have public support for it. But then when you have 1,000 people and they're all paying a small amount, then you can afford it. So it's a win-win situation. So you go from 1820s or so, where there's the first trains, and within 30, 40 years, there are trains all over Britain and then all over the world. And you get this incredible kind of story, Jules Verne's story of Around the World in 80 Days, where the hero tries to get around the world in 80 days and has all these railway timetables, and is getting onto steam liners at sea, and then getting off and then getting a train across. And it's also a thriller aspect to it. But the main thrilling thing is capturing the fact that the world has suddenly opened up, not just to the soldiers of the world who were already traveling the world, and the sailors, and mostly dying or getting disease or whatever. This was liberty for everyone, potentially. And that's what the book did around the world. It said anyone can travel the world in relative safety and relative comfort. And so that's an amazing moment for steam and the railways. And people fell in love with it. 100 years of extraordinary adventures for everyone there. By the way, the holiday is then born, because before that, the holiday is a steam invention, because before that, most people are living on the land, and they don't have very many holidays, but they also don't have any. Where would you go? I mean, you can only go to the local village. You can only go where a horse will take you. Like, there's nowhere to go. You know what your village and your local countryside looks like, right? You can go on a pilgrimage. That's a different thing. But to go on a holiday as a family, you need a mode of transport. And these trains, just going back to them, these trains went to the seasides. And then the seaside towns started to stop being fishing villages and started being these places that catered for this increased wealth. So it's an incredible thought that the trains, they just bring liberation and holidays to everyone. And all right, they bring a lot of smoke and dust, but they bring a lot of joy too. And the liners, the ocean liners, also then start taking on this idea of a holiday. And so you get these really massive ships, and they're no longer got sails on them, and they're luxury. And this is the way, if you're rich, this is where you travel the world. And these things, the first class cabin in these were, like the Ritz. I mean, it's an extraordinary to look at them. They had every mod con you could possibly want, all powered by steam. And there's extreme excitement about it all. So yeah, I'm just going to sort of stop there. There's more to say about where steam went, but this was sort of the high point of steam. The railways, the ocean-going liners, and the steam-powered electricity generators that then brought electricity to everyone. It was a sort of high point, because there's a point at which the steam car, I haven't come back to that, but the steam car happens because the infrastructure for making good roads happens. And just at this point where the steam car would have been the dominant form of transport, the internal combustion engine arrives and outclasses it because of a lot of, it's still a gas technology, but it's not a steam technology. And in a way, it's a shame for all those steam car enthusiasts, because they are beautiful things. But yeah, in the end, we ended up with diesel and petrol cars. I just want to also just slightly change gases, because that's a very industrial kind of transport kind of centered view of a gas. But with industrial Britain and growing industrial world, there's a lot of people in the cities, and a lot of them are dying of respiratory diseases, and so all sorts of medical applications for gases start to become interesting. And a guy called Beddoes ends up opening something called the Pneumatic Institute in Bristol, a city in London, in the UK, and is trying to solve trying to cure some of these diseases, because they're completely widespread. I mean, tuberculosis was killing millions of people all over the world, and still does, actually. And they just didn't understand that it was a bacterial infection of the lungs, and they didn't understand, they had no thing, but they were just trying different gases. And a guy called Humphrey Davy is a young scientist, is employed to just start experimenting. And he gets hold of, well, first of all, he tries carbon monoxide and almost kills himself. Then he tries nitrous oxide, which was also thought to be toxic to the body, and is toxic. But it also does something else, which he noticed, was it makes you laugh. And he sort of giggled and laughed and couldn't believe it, and thought, well, maybe it cures tuberculosis. So he tried it on his patients. It didn't cure tuberculosis, but they did laugh. And then he started thinking, well, I wonder what else it does. I mean, maybe it doesn't cure that disease. So he starts inviting poets and other people in just to try it, and he has all these parties. Everyone loves it, and they all get high, basically. And he writes lots of poetry about it. And then he notices something, like a good scientist. He really notices something really unusual about it, which is that it is an anesthetic. It actually does basically make the nerves unresponsive to pain. And that is an unusual thing. Like, there are lots of things that make you drunk, alcohol. There are lots of things that get you out of your mind, like opium, and they were widespread at the time. But they're not anesthetics. You still thrash about. If you go into surgery or go to a dentist and you're drunk, you'll still thrash about in pain, and that's no good. It may sort of make you less worried about the procedure, but it also might make you very sick. But this was not one of those. This was an opportunity to make someone actually calm and desensitized to pain. Now, the funny thing is that then, for a series of reasons, Humphrey Davy stops working on this. And one of the reasons is undoubtedly that he really wanted to be a serious scientist, and ended up being a prolifically impressive discoverer of new elements and incredible scientist. And he goes to the Royal Institution to do this, and he's offered a position there. And he's pilloried in the press, in the British press, which is famous then and still is now for being, for just not letting anyone of any note off the hook if they are taking themselves too seriously. And they noted that these laughing gas parties, well, they were like, ridiculous, and why were people doing this, and this isn't proper science. And so they sort of ridiculed them in the press, and this is a cartoon of one of them. And to his credit, he took this in good faith, but he basically understood that you had to be really careful about what you worked on if you wanted to be considered serious. So he stopped working on laughing gas as an anesthetic. There's another reason, of course, which is that the doctors of the time weren't interested either. You would have thought they would be, but they were sort of convinced that anesthetics were perhaps unhelpful because you needed pain to get the medicine to work. That pain was an important part of healing. And if you didn't have the pain, then maybe you wouldn't get healed. So they weren't particularly interested. So that's the end of his relationship with developing that as an anesthetic. But other people took it forward, especially in America. A guy called Colt started touring America. He wanted to make his gun, the Colt revolver, and he needed to make money, so he pretended to be a doctor. he did all these laughing gas demonstrations where he'd get people onto stage, and they would come up onto stage, he'd give them laughing gas, and then they would do all sorts of funny things. You couldn't really predict what they were going to do. To get someone who's very prim and proper on stage, and then, yeah, they would just recite poetry or become a small boy or whatever, and just people found this hilariously funny, and they would come along, and everyone just was very jolly. And he kept doing all that until he had enough money to make the Colt 45 a reality. And the thing it did is it kind of made people aware that this substance existed, and you could make it quite easily. And so lots of people started experimenting with it, including some dentists. And the dentists got hold of this and started trying to work out if it would really help with dentistry, like to make people insensitive to pain and therefore have dentist operations. And that was a shaky start to that, but in the end, that is one of the things that sort of took off. But they weren't sure that nitrous oxide was the best gas, so they started looking at other things too. So they tried ether, and ether worked quicker and more effectively. And so they also experimented with imbibing ether through these breathing apparatus. Now, ether is intoxicating in the same way that alcohol is intoxicating, as well as being an anesthetic, and can make you very sick. So you have to really get the dose right, and getting the dose right of a vapor with people of different physiologies and different sizes, that was that's the beginning of anesthetics. That's the beginning of being able to do this reliably to order. And then, of course, people got hold of other things. And this is a diagram of a guy called Simson, who is in Edinburgh, and he's a doctor, and he's every week they experiment with a different vapor to see if they can find one that does some interesting thing. And one evening, he and his friends imbibe chloroform, and they all collapse, and they wake up the next morning with a hangover, and they go, "Oh my God, this is amazing. Maybe this stuff is like, this is the perfect anesthetic." And so he tries it on his niece, and she starts singing and then collapses, and he thinks, okay, this is perfect. So they start rolling this out and start using it as an anesthetic for childbirth. And lots of people are appalled. Like, the idea that you should have any pain relief in childbirth was thought to be, again, as I said, would stop the mother bonding with the baby. All these kind of spurious reasons were given for why this was a bad idea. And there was lots of debate in the press about it. And in the end, it's only when Queen Victoria uses it for one of the birth of her children and says it's so brilliant that it gets the royal seal of approval. But nevertheless, it's actually a very dangerous thing to sort of use. And if you get the dose wrong, you can really harm the patient. People were dying as well. So like a lot of these things, it was both a boon and a danger. And at the same time, you had authors, people like Agatha Christie and Sherlock Holmes, Arthur Conan Doyle, were suddenly understanding that, okay, these substances can become part of our plot line. So we can get our the use of chloroform can just knock people out, and you can just put chloroform over someone's head, and then you can abduct them. And so this becomes a plot line in lots of detective stories, and then it becomes a real thing. People actually try it in real, like real baddies start trying to mug people with chloroform. And what they don't realize is that in the stories, it's kind of takes 10 seconds to knock someone out. But in reality, it's much longer than 10 seconds if you're not going to kill them. And so there's stories in the press of the time where people are, have a hand clamped over their face with chloroform and they struggle free. And because the person doing it to them had no idea, thought they would just become senseless within seconds. So there's lots going on culturally around these substances and the idea of anesthetics and vapors. And this is a cartoon back in the Royal Institution where Davy was practicing, just showing like the kind of attitudes of the public to these different gas experiments and the use of them, and how ridiculous the whole thing was and how stupid everyone is, but also kind of enjoying it. There's a real sense of knowing enjoyment about this cartoon. Like, this is the future. Like, we can muck about with gases, we can get them to do all sorts of funny things. And in the end, laughing gas is the gas that persisted to this day as a pain relief. And if you go into labour as a woman, you will often be offered gas and air as a very, very effective way of and the reason why it sort of works in many instances, if you're a paramedic, paramedics all carry nitrous oxide with them because it's very easy to apply. They're on site. It's just a mask. You can self-regulate, so you can tell people how woozy you're feeling, and it's quite mild actually in most cases. And although you can have terrible toxic side effects, in general it is pretty safe. So yeah, nitrous oxide. So that's it's just a kind of incredible story of the kind of development of our relationship with gas and pain, toxication, cultural norms, detective stories, everything. It encompasses the whole of human life. I'm just looking at my time, and I've actually, yeah, I'm running out of time slightly, aren't I? Well, I think I'm just going to do methane because I think this is another really great story in the book of a gas that we start off kind of associating with spirits, right? So the will-o'-the-wisps in the woods and jack-o'-lanterns, and in every language there is a name for these weird misty blobs that end up lighting in fires in marshy landscapes. And over time, after a while, people start to realize, Victorian time, they start to realize actually this is a real gas and it's methane, and maybe we can do something with it. So they start to think about, well, couldn't we just make methane from coal, because we've got plentiful coal, and then we just ship it around a city and we can use it to light the city? And why should lighting the city be such a kind of important application? Why should that come before heating or cooking? Because it came way before those. And the answer is that the cities were really dangerous at night. Like big cities like London, New York, Chicago, Paris, all the big cities were incredibly dangerous places at night. And people were mugged and raped and killed and thrown in the river. And, you know, just if you got lost at a city, you were in real, you know, fear of your life. So people stayed off the streets in the evening unless they were ne'er-do-wells or unless they had security. And this was not healthy, and people wanted to own the cities at night. And so lighting was thought to be the way forward, a real enlightenment moment. But how to do it? Well, here was an opportunity: methane. Let's pipe the gas through the city, up posts, and then light it. And you can see they had a go. And these are the first, you know, in London, it was the first streets were lit by gas, and this is a gas lighter, and that was a real job. And there was also a job which was to look through the windows of some of the private clients, because the first clients were you know, the cities themselves, and people started using them indoor, and then you had to look through the thing because they didn't have meters for it. It was just whether they saw whether you used it at night or not, and then they charged you. And people stole it, and it leaked, and there were explosions. But all in all, people wanted this dangerous gas in their lives, in their cities, more than the associated dangers, which were appreciable. And I guess the reason why they chose to go down that road, and it was a sort of, it wasn't a done deal. Like when it's about 1812 when the first street is lit with methane gas. Once people get experience of it and they see these beautifully lit cities, I mean, we're so used to them now, but this was you've got to remember that these were dark, dangerous places, especially in the winter. And suddenly they weren't anymore. They were lit. They were glorious. They were a celebration of light, and people could go shopping. And you shouldn't underestimate the commerce aspect of this. Is that people were safe to go out at night, and therefore they were safe to go and enjoy themselves, go to parties, and so the nightlife, the city life, the shops, they were all benefiting from this civic infrastructure, this gas. And so in the UK, the first streets are lit around 1812. By 1826, every city in the UK over 100,000 people has a gasworks. I mean, I mean, that's an incredible rise of a technology. It's happening alongside the railways, and everyone's very excited about the future. And you have this idea of a utopian future where technology is really kind of helping everyone, and the cities are on the rise. And so this is an example. To our eyes, doesn't look like a utopia. These big structures in the background, that's where they stored the gas at night. Sorry, during the day. You store the gas, you basically produce it in a gasworks. So every city had a gasworks. They had these structures in them. They were usually on the outskirts of cities. They were pumped underground, all the gases, up the lampposts, and then they were lit by hand. And these enormous amounts of gas were stored during the day as they were producing the gas. In these gasworks, in the end, it was called town gas, and it was a mixture of carbon monoxide, methane, and hydrogen. And yeah, this was the backdrop of so many people's lives, and it was seen to be progress. And we're used these days to having a completely invisible infrastructure, but we're still having to put up with the fact that methane is a very dangerous gas in our lives. And there's not a week that goes by, if you look at the global media, that there isn't a big gas explosion somewhere and whole houses, blocks disappear. So we haven't quite tamed the will-o'-the-wisp, and we're still very reliant on gas, not just to generate electricity, but also in our homes. When the Putin started to wage war against Ukraine a few years ago, the gas prices went up through the roof in Europe, and that caused enormous political crisis across Europe. Just the one commodity, methane, has so many ripples throughout the economy, and the huge inflation followed and huge problems followed just because of this one gas. Even though now our streets are not lit by it, but our central in central heating, electricity, and hot water, these are all linked to gas. Do you know what? I've realized I'm sort of getting to running out of time, and I was going to talk about hydrogen. I thought I'll just give you a glimpse of the slides, and we can ask questions. The first hydrogen balloons were very early in the 1700s. So the first balloons were not hot air balloons; they were hydrogen balloons. The US military used them as observatories in the Civil War. Here's them making it with using sulfuric acid and iron filings, and they would go up in these hydrogen balloons and have a look where the opposition was. Then the Zeppelins come along, First World War, and they start dropping bombs on cities, and it's terrifying. Then peacetime comes. This is a Zeppelin over called the Zeppelin USS Los Angeles over Manhattan, and everyone thought the first airlines were Zeppelins, and everyone thought that the future of air travel was Zeppelins. Everyone thought it. There was no doubt that this was the way to go. But unfortunately, disaster followed. Hydrogen, of course, flammable, although an amazing gas, and so light, so incredibly low density. And of course, there is the rise of the fixed wing airplanes that takes over on the air flight. And the noble gases, this is the story of finding helium, or the spectral lines of helium in the sun, thinking, what could that be? We know that there's hydrogen in the sun, the calcium in the sun, but what's these new lines? We've never seen that element before. And Mendeleev coming up with a rudimentary periodic table, and two scientists starting to measure very carefully gases and realizing that there's some anomalies there in the air we breathe. There's another gas that no one's ever seen before. And then in the end, nailing down the fact that there is this gas called helium. It's in the sun, but it's also in the earth. There's argon, it's 1% of the air we breathe. It doesn't react with anything, which is why no one had ever seen it before. But there's also neon, which is a very, when lit with electricity, very bright, and krypton and xenon. And so you get neon lights, you get, again, the cityscape is reborn, but this time it's party time. It's the next level of civilization, all brought to you by these noble gases that no one knew existed until the early 20th century. And the periodic table has to be remade to put them in. It's in now group 8. And they discover gases like radon, which is heavier than lead, but it's still a gas because it's so unreactive. It won't even bond to itself. An incredible story. And oxygen, just to say that, the early Earth, this is what early Earth looks like 4 billion years ago. Not blue, but orange. And the reason it's orange is because the early atmosphere is methane, hydrogen, nitrogen, carbon monoxide, all boiled up from the Earth's surface, the lava-strewn surface. It's a very active planet. But we, unlike Mars, we hang on to our atmosphere because of a magnetic field, so we can deflect the sun's winds, and so life starts. But there's no oxygen. There's no oxygen in the early atmosphere, and it takes billions of years for oxygen to arise in the atmosphere. And we're pretty sure the only reason oxygen comes is because life starts on the planet. So when life starts, you get these little bacteria that are kind of consuming energy from the Earth, and then you get this event about 1.5 billion years in, where there's a new cyanobacteria that does photosynthesis. It takes energy from the sun and carbon dioxide, and it emits oxygen, and suddenly there's a massive rise of oxygen in the fossil record, and it's called the Great Oxygen Event because it kills off loads of life, because oxygen is so reactive. It reacts with everything and just kills everything. It's toxic. And a whole set of bacteria have to develop that can cope with an atmosphere that's oxygen rich. And that sparks a new evolution of life, a new phase of life, which is much more complex. And every time you get a spike in oxygen in the last few billion years, you get new life. And it's only when oxygen reaches a certain level, the levels we see today, like 20%. So you're going from almost 0 to 1% in the Great Oxygen Event, and then to 10%, 20%. It peaks at 30% and then comes down to our current levels of 19%. But it's only because we have that level of oxygen in the atmosphere that we think that complex organisms like that have enough fuel to run our metabolisms, to be as big as we are, as complex as we are. So oxygen is this important. I mean, it's not just obviously important because we breathe it, it's important evolutionary wise, because it spurs evolution to make ever more complex things because of the power of the energy inside that molecule. Anyway, I hope that's given you a good sense of the book and the kind of way in which I approach the subject, sort of looking at all different sides of the different gases. I haven't told you about the chapter on smell. I haven't told you many other chapters on different aspects of gases. There's a musical instrument chapter, of course, because, you know, such gas technology, music is vibration of a gas. So, but, you know, it didn't have time, but we can perhaps talk about it now.
Thank you so much, Mark. Wow, we've covered loads there. Yeah, unfortunately, yeah, we did run out of time but you know, luckily you've got a book available, so people can go out and buy that book, and it's all there. And I have got an early copy. I say it's absolutely brilliant. I think I mentioned when I met you last week, love how you start each chapter with a little story about your life and your past, and that's really fun. And I'm still looking back thinking, how on earth did you feed that into the chapter somehow? But somehow you have, and you've linked it, and it's brilliant. So I'd say, yeah, for anybody interested in what they've heard today, please go and buy it. It's a really good book. I'm sure it's going to do fantastically. We have so many questions. I fear we may not get through them all, but we're going to do our best to do as many as we can. I'm going to start with a good one, actually. You haven't mentioned CO2. A great question. What's your position on climate change caused by anthropogenic CO2? And how can we address it? Not a small question. I'm sorry, if we can keep the answer as short as possible.
Yeah, no, okay. There's a chapter on CO2 and it does address this question. I felt I couldn't not. Obviously, it's the most, in a way, it's the most important thing to think about CO2. Is that we've got climate change is undeniable, that the Earth is getting hotter. And in the book, I focus on the small island states. And I hope the book is really empathetic more than anything else. Like, I feel like our relationship with gases is about sort of trying to improve the human condition for everyone. And when you look at the island states, there are people being born now on small islands, which they're never going to be able to live there for the rest of their lives. They're already at the point, the Maldives, for instance, they're a meter above sea level, and the sea levels are rising so fast. So we really have to help them. That's my feeling. And the question is, how do you help them? It's really more complex than you might think, because in the case of the Maldives, they're building upwards. They're actually trying to stay on their islands, which they've been there for thousands of years, and they're building upwards. But in order to build upwards and protect themselves from this, basically build faster than the sea level rises, they have to fund that. And guess how they fund it? With holidays. And guess how people arrive? By plane. And guess how big CO2 emissions by plane will be in 10 years' time? a huge amount of global CO2 emissions, because if you look at the way in which more and more people are flying, and at the moment it's 2% of CO2 emissions, but as renewables start displacing electricity in the areas we can decarbonize, you're going to see areas like plane flight come really up the agenda. And the weird thing about plane flight is that many people rely on it for their income and for the way they do business. So it's really difficult to decarbonize flight. It's going to be really hard. And the one that I really focus on is that we have to tax it higher, because we're going to need to fund decarbonization of flight, and it's probably going to be carbon capture of some sort. But we're in the early days of carbon capture, so we need money to funnel into it. I know that we're ingenious enough to sort it out, but we need money in there. And it turns out there's a really weird anomaly with aviation fuel, which is kerosene, which is it's not taxed. So flights are artificially cheap, and that then fuels further flights. So this is, I guess, in a nutshell, the issues I consider in that chapter on CO2, which is that it's actually about the fact that we're going to have to do something fast. We need to funnel money into it to get to release all the ingenuity that I know we have, and that has to be via taxes on flights. Flights need to get more expensive.
Yeah, absolutely. It can be very cheap to get around the world, can't it? If you get the price.
Yeah, we're not factoring in future generations.
No,
we're just not factoring it in.
No, absolutely. Okay, thank you. A question from Magda, which is a great question. Was there a gas you wanted to include in your book, but for some reason you didn't include?
Yes. Now, that is so true. And now, why has it gone out of my mind? Because that would belie the fact that I really wanted to do it, wouldn't it? There are so many. It's so hard to choose. Let me come back to this.
Okay.
It's going to pop into my head, but there are loads of gases that I wanted to include. Yeah.
And I was going to say, I'm so glad you did get on to speaking very briefly about the noble gases, because they are my favourite gases.
Yes.
And yeah, that's great to learn about them. And yeah, seeing how important they are in our Earth, that they were there right from the beginning. And yeah, they're actually continue to be really important gases. And of course, because they're inert, they're great fun. So yeah, thank you for covering those. And I was going to mention something about the laughing gas as well, because it's commonly in the UK anyway, it's very commonly used in childbirth. I actually gave birth in the US, and it was only about 8 years ago. And they said to me there, oh no, we don't use laughing gas here. That's what they used in the 1950s. You see, I don't know if that's the same across the whole of the US, but it's seen as a very unregulated drug that you wouldn't just give it to somebody, because what might happen, because it's a much more controlled and medical environment when you give birth in the US in general. So that was really interesting, because I was a bit disappointed. I was like, what? I can't have, this is something all my friends talk about in the UK, and it's not something I've ever experienced. So yeah, I mean, I hope I never have to experience using laughing gas, because it would probably mean I'm in pain. But yeah, they don't use it there. So I'm not sure again if that's everywhere, but it was where I was. So interesting.
Yeah, and it's well, it is. It's also from a climate perspective not a great gas. It's a very strong global warming gas, unfortunately. So breathing it out is bad. And it's obviously they do use it in America and many other places in the world in another form. And it was invented for this form, the technology in America, which is squirty cream. So if you squirt cream onto any cake, and it happens in every restaurant, I can tell you, they use laughing gas as the propellant. And the reason they use it, and it's in the book, it's a great story as well of an accidental discovery, is that it dissolves in fat, the nitrous oxide, and so it can sit in the liquid, and then when you release the pressure, it bubbles up, so it immediately makes cream fluffy, and it's not acidic, so it doesn't make the cream, which is unlike CO2, which you could have used perhaps. And also it embodies fluffy cream, right? Laughing is a delightful substance, right?
Indeed. Okay, that's great. I like that fact. That's a good one. Okay, a question from Sean. What is your favourite gas and why? It's a funny question, isn't it? But I think we're in a room where we're allowed to talk about our favourite gases. So go on. What's yours?
Well, I mean, I think laughing gas is one of my favorite gases, but you know, I also think that steam, I have to say, it's just so weird. I tried to demonstrate this last night in a live lecture. The sound of a steam whistle, like, and steam going, I find it just really alluring and just nostalgic, and you know, in a way that I don't find diesel cars, or even like when you have that, you know, I'm sorry, people will disagree with me about this, but you get these people who've got these cars that have got these amazing V8 engines, and they go, and obviously people get off on that and they think it's great, but it doesn't do anything for me. But a steam engine, I love them. There's something very human about the size. It's something to do with the auditory range, the size, and it's like an engine that's much more human.
I like that. No, I think also, yeah, it's that old school feeling, isn't it? It's that, yeah, when, you know, and I think I remember the Railway Children was one of my favorite movies when I was little, and had those steam engines all in it. And yeah, that noise is amazing. No, I like that. That's a good one. Okay, who have we got? A question. What's the most surprising fact you discovered when researching the book?
Yeah.
Probably a hard one.
I mean, there were a lot of surprising facts. I think, okay, I'll give you this one, which I was astounded by and had to go and check it several times because I just thought it can't be true. You breathe 12 kilograms of air a day. 12 kilograms is how, you know, and if you think about how diffuse air is, how light it is, it just tells you something like this sense of that this stuff, however light it, has a weight, and the weight bears down on you, right? 1 kilogram per cm squared on you now, right now. And we're able to cope with it, and you're breathing in 12 kilograms. It's extraordinary.
That is amazing, isn't it? No, that is quite hard to really imagine, isn't it? Because you're just like, air is nothing, and you're like, oh, yeah, okay.
It's a substance, and it has weight, and we actually need loads of it. Yeah, and while writing this book, I mean, I used to be someone who, I suppose, I kind of didn't notice. I would only put the window open at night if it was hot. Then I would put the window open, sort of to cool the air down, I suppose. And now I have the window open, hot or cold, because I realize that actually, if the oxygen levels dip in the room that you're in, not very, very much, your physiology is really impaired quite a lot. You cannot withstand much difficulty. And so it makes no sense to sleep for 7, 8, 9 hours. No, I never get 9. 6, in my case, 6, 7 hours. 7 is probably the max. I've got small children. But anyway, it makes absolutely no sense to sleep in a room without fresh air coming in. It makes no sense. You will get much better sleep because your physiology is not struggling at all, at least with that side of things, if you have the air window open. So everyone.
But what about if you live somewhere that's very polluted? Would you want to do that on a main road? I don't know if that's worse then. Okay,
well, that's the other thing I did as soon as I started writing the book. Is I got an oxygen meter and a carbon dioxide meter and a VOC meter, where they're all in one now. And VOC, so these are volatile organic compounds, and so they're off gases often from things like, you'd be surprised, carpets, sofas. There's lots of things that are giving off vapors the whole time, and you're breathing them in. And some things, let's say a new item comes into your house, you put this meter by it, and you see it go off the scale, and you are so shocked because it's all invisible. And yet some of these things, just because of the manufacturing, and no one tells you, no one's they're actually, and it's not everyone, but there are some manufacturers you just got to keep an eye on. So yeah, I have also become sensitized to the pollution thing and particles in the air. Yeah, you become just ultra sensitized to the invisible stuff that you're breathing every time. But I do think, yeah, mostly I think fresh air, you know, fresh oxygen probably is the thing I mostly want. I don't want high CO2 levels.
Yeah. Yeah, and we've learned all about that in COVID. A lot of us are more aware of, you know, having fresh air and not having too much CO2. Yeah, the VOC thing is interesting. Some people are very, you know, can be very allergic to them, and it causes them lots of troubles. And yeah, I had some new carpets fitted years ago, and for the first week or two, I couldn't stop sneezing. It was horrible, and I discovered it was probably the glue they used or the carpet itself that was giving off. So we just had all the windows open. But yeah, that's the first time I sort of learned about what it could be from immense Googling of why on earth I was reacting. Okay, we probably only got time for a couple more questions. There's a great one here talking about to the musical instruments, which we didn't cover. So this is a question, so just like sulfur hexafluoride deepens the human voice, can it be used in musical instruments such as in a violin to make it sound deeper? I don't know, this is quite an interesting question.
Yeah, so the soundboard on a violin, these are vibrating pieces of lightweight wood, and so the whole room would have to be sulfur hexafluoride, right? It wouldn't just have to be inside the violin. That's the thing. And so the frequency that you're getting would have to be the whole room, and you'd then die. You'd maybe die listening to a very exotic piece of music, but that would be bad way to go. It's also a really bad greenhouse gas. It's another one that's really bad. So yeah, but I think the equivalent of that is musical instruments underwater, because then you are hearing a completely different vibrational kind of elastic modulus, and yeah, as we know, you get completely different sounds underwater, and it stifles some and brings out others. But yeah, that's a good question. It's an exotic gas, definitely. I still haven't remembered the gases I wanted to do. Why is that? I think I must be, I feel bad now. There are definitely lots of, I mean, it's just the world's full of amazing gases, actually.
Definitely. Okay, well, thank you so much. I'm afraid that is all we have time for today. It's been a whirlwind of gases today, and that's been brilliant. So thank you so much, Mark, for joining us. You've been wonderful, and I'm really excited about your new book that's out. It was absolutely fascinating talk, so thank you so much. And thank you to our audience. You've been really, really busy in the questions box. I'm really sorry if we didn't get around to putting your questions, Mark. You can get hold of him on Twitter and various other platforms. So, you know, if you've got a burning question, please send it over to him. But thank you for putting so many fantastic questions in. Again, if you missed anything today, you want to go back and watch again, wait for an email in your inbox, and we'll send out a recording of the webinar, and it'll also be on our webpage. And if you've enjoyed this webinar, then please do check out chemistryworld.com/webinars. We've got lots of future events coming up throughout the year. But that's, yeah, as I said, all we have time for today, and I look forward to seeing you again in a future Chemistry World webinar. Thank you and goodbye.